Okay, welcome back, everybody. We're going to get into the most exciting part of the day with the deep dive into technology. And for once, I'm not going to be the nerdiest person on the day because I've brought two guests with me today that will take a deeper dive into technology. No, it's okay. Today I'm going to take it easier for sure. So, we're going to talk about inspection technology, consideration, and applications today. And we're going to cover a wide array of this, from inside of your own facilities, what's going on with your current technology, what's on the horizon, what's upstream, downstream, and then some further insight into what makes FlexXray's technology and how we leverage that work for you whenever you're having foreign material incidents, or to get better at some of the themes of the day, supplier monitoring, or ensuring that your own systems are working like they should. First thing though, Moore's Law. In case you haven't heard of this, this was the Intel founder created this in 1965. And essentially it says the number of microchips, the number of transistors on a microchip is going to double roughly every 2 years. And he made this statement in 1965 and it's held true. And in fact, we probably have less than 10 years left on the runway for this. But this statement really enables all of the technological advancements for us today, from our cell phones to an X-ray or metal detector. Every few years, we're able to process more and more data quickly in order to be able to advance technology. So that's the theme that's driving everything from a simple metal detector improvement, an X-ray improvement, all the way through AI and machine learning to today. So the first thing I want to talk about is a little bit about what's at your disposal in a food plant for detection technologies. And a lot of these things you know really well. You've known metal detection for 50 years. You've known X-ray inspection for the last 30 years. You may not know as much about hyperspectral imaging. You may not know as much about microwave inspection. We'll do a little bit of a deep dive into some of those. And then CT inspection is where we're at from a FlexXray perspective in our advancements with X-ray. It's still X-ray technology at the end of the day, but we're able to do a 3D evaluation here. And I won't go into every single one of these benefits and limitations. Obviously, a metal detector is purpose-built for metal inspection. It's still the best thing out there for metal. And in fact, if you have aluminum that's a potential risk in your production environment, do not get rid of your metal detector, please, for the love of God. Don't throw it out and replace it with anything else. Either that or get rid of all the aluminum in your production environment first. From an X-ray standpoint, I'm going to take and slice X-rays up a little bit further because we've come so far, so fast with X-rays in the last few years that just talking about X-ray in a functional silo doesn't make any sense. We've got to talk about TDI and photon counting and single and dual energy and all of these things all at the same time now. So we will take a few minutes to talk about that a little bit further. From a hyperspectral and microwave standpoint, if you're not leveraging these opportunities upstream in your production environment, you're missing a big opportunity. Hyperspectral imaging, there's Christian from P&P Optica is in the room with us. Sorry, I can't, thank you, sir. If you want to have an introduction with him later, I have one slide over there, stuff I cannot do it justice as it relates to exactly what it can do, but qualitative analysis, and to be able to do material discernment of low density plastics, wood, those types of things. It is on the surface, so it does have limitations, but it's a fantastic piece of technology and you definitely should leverage it whenever you have opportunities. Similarly for microwave technology, that technology's been around for 10 to 15 years now, but the advancements that they've made at Food Radar over the last few years to improve this, to remove the vacuum from the line as it's going through, they can produce a qualitative inspection on more products that aren't just straight homogeneous matter. Like it can have inclusions and other things in it now and still find a functional detection. We're going to take a deeper dive into that later as well. And then CT technology, it's really unlocking everything about X-ray, making that a 3D inspection. It does have limitations. A gantry is huge. We're spinning, if you've this white light feature in the back of the room, that's like the size of one of these devices almost. And so we don't really have room for that in every one of our production facilities at the moment. So quick dive into a few of these technologies. I won't belabor metal detection because it's been around for so long. Wet mode, dry mode, we're using conductive signals and magnetic signals in order to make a determination of the location and size of a potential foreign object. We're disrupting the base signal that the food product presents as it passes through. That's our signal that we're creating as a baseline whenever we set up sensitivity levels with a metal detector. And in fact, for the better part of the last 30 plus years, your internal maintenance staff has been adept at being able to configure a metal detector to adjust sensitivity levels, to change as your product changed or your SKUs changed. And as we've advanced further, from a Moore's Law perspective, we've gotten very technologically advanced with our detection schemes. We've lost some of that in our own maintenance departments. Now, I feel like I'm not adept at times understanding some X-ray and imaging science stuff to the fact where I have a PhD person on my team now that helps me with all of that. From an X-ray detection standpoint, I do want to make sure that we understand all of the technological differences within an X-ray. An X-ray is not just an X-ray any longer. In fact, if you have the opportunity to replace your X-ray systems and you're not going all the way to photon counting right now, then you're missing out on the best possible advancement in X-ray detection that's happened, and really, I would say in the last 3 years, it's been fully leveraged by almost every vendor for an X-ray. And we have the privilege today to have a guest with us that I think leverages that technology the best, and so I won't steal all of his thunder later as it relates to photon counting. But we get the highest material discrimination there. Speeds, it says medium, and with everything from a technology standpoint, as we go down in the detector pixel sizes, yes, there's so much data that we're trying to process, but we're bending pixels together. There's other shortcuts that we can make whenever we're processing image data to keep up with production speed. So there's technically nothing that's here that has a limitation as it relates to speed. We just change the way that we process data in order to keep up, whether you're running 100 feet per minute or 400 feet per minute. We can process all of the data that you need to as it relates to an inline X-ray. Unfortunately, oftentimes I think we feel like we're being sold by a manufacturer, whenever we get ready to install a new X-ray, and we're not always doing the right due diligence with a good gauge R&R analysis of these things to understand exactly what we're being sold. So when somebody comes and approaches us from a food perspective, we can find stainless steel down to 1 millimeter. Well, that's great. Technically, the detector can find that down to 1 millimeter. It can find it down to less than that, but that doesn't mean it can find it in our production environment, in our speeds, with our materials, things like that. And so doing a better job on the front end with our quality engineering teams, our maintenance groups, things like that, understanding that everybody's getting out of a new installation what they need as it relates to that, because we deal with a lot of customers over the last few years that have purchased new equipment and it did not perform the way that they wanted it to. And I can probably go around to everyone in the room that has a similar experience with an X-ray or some other device. It might be just a case packer or a palletizer. It doesn't always deliver exactly what we want it to. Photon counting, to add to this before we get away from it, the best things about dual energy exist in photon counting. We can do multi-energy discernment. The best things about TDI exist in photon counting. We're doing time delay integration with photon counting as well. So TDI, quick explanation for it, the old version of X-ray, whether that's single energy or dual energy, every row of pixels is taking and averaging the same data. And we're just averaging 5 sets of data or 6 sets of data, whatever the number of rows of pixels that we have. With TDI, we're adding to that computational power by passing that information to the next set of pixels to improve the overall accuracy of the data set. That just gives us better image quality overall. We combined that with dual energy and with TDI and photon counting, and we eliminated a ton of the noise. We'll talk about that in just a little bit. I'm sure the word like scintillator was not on anyone's bingo list today, but we'll talk about scintillators for a few seconds. Before we talk further about what goes on at FlexXray with our detection technology, I want to talk a little bit more about what happens with hyperspectral imaging and with microwave. So from a hyperspectral standpoint, there's so much data being evaluated across all of these different bands from an NIR perspective, near infrared, that we can do a host of things. So we can be more precise as it relates to understanding what a foreign object is, we can be more accurate as it relates to its location, and we can be more sensitive as to the sizes of that as well. Because of the way that this works, we can also do qualitative analysis, fat, moisture, protein analysis on the fly while we are doing hyperspectral analysis. So if you were a ground beef or a ground chicken producer and you have a trim table set up, if you are running that trim across this device from PMP Optica, you can understand exactly what you're hitting as far as your targets post-grind up front, so that you can add more lean, add more fat to the process, improve that yield before having to go pull a sample and take that back to the lab. Obviously, this surface detection only, anything that's imaging based. Microwave detection, I'm going to let Andres talk a lot more about this later, so I'll be very, very quick as it relates to this. This is the device. It looks very simple. It installs very cleanly in any pumpable production environment. I don't want to speak for his advancements over the next couple of years, but I think there'll be advancements that allow for this detection in ground beef, ground sausage types of environments eventually as well, to be able to handle and push that through the microwave chamber for detection there also. It's fantastic because it's using some properties, dielectric properties, which we'll talk about a little bit later, to infer things about the baseline of the product, and anything that disrupts that signal is potentially foreign, and that the way that they're doing that has redundant settings in there, and the air zip, again, I'm already speaking too much about his technology. I find it fantastic. We have them on site in Texas at our facility for his US team to be able to do sample testing for any of you. So if you want to learn more about this and you're not ready to install a demo unit inside your facility, we take drums and 5-gallon buckets and pour them through the device with a host of foreign materials and do demonstrations at our Texas facility for the Food Radar team. I'm going to go back to what Ken was talking about earlier today, and this is kind of the big theme of yesterday's conversation as well, is that how do we really validate our existing programs? And that could be a supplier monitoring program, that can be just our programs in line right now with their own X-rays or metal detectors. But we can't properly validate if something is working like it's supposed to if we're not testing to below that standard to a certain extent. So if everything that I'm supposed to do with my own internal X-ray or metal detector is at 2 millimeters from a stainless steel, just to pull a random number, if I don't inspect that below that standard at some point in time and challenge that, I'm not truly verifying its functionality to make sure that it is detecting everything that it's supposed to be. And every time that you've ever had a consumer complaint, every time that you've ever had a finding on a magnet or a metal detector or an X-ray, it's never been a spherical shape in the history of detection for foreign objects. So it's going to present amorphous shapes. Unfortunately, from a statistical standpoint, we can't do a gauge R&R study and know the efficacy of our devices on amorphous shapes, because they're going to present themselves different orientations, fashions, locations, things like that. So the best way to understand if the device that you're only challenging with the spherical seed at 2 millimeters is to do that at a lower seed size, because then we can pick up things like those amorphous shapes that you may or may not have missed or found whenever you were inspecting previously. So at FlexXray, it really boils down to one thing. We slow the process down. And if you've been lucky enough to walk into one of our facilities and watch paint dry on a monitor for a few minutes while the product passes in front of our flat panel detection technology, which is a manual inspection, we'll talk a little bit about exactly what that looks like in a moment. It's very slow. It's 3 to 5 feet per minute. And when you're used to watching product go down your conveyor belts at hundreds of feet per minute, and a human being is standing there looking at a monitor, it's painfully slow. But that's how we're able to find things. Not just because of the speed, but you can get more photons from an X-ray physics standpoint through the product if we slow everything down. The more photons that we present to the imaging device, the better contrast, the better quality of the image overall, and we can discern foreign objects from things that may be more indigenous, like cartilage, sinew, bone, things like that we may not want to reject all of that in a product matrix. And everything that we do is fully customizable. So when a vendor sets up your X-ray, they're really setting up a configuration at a speed, detection parameter, something that's meant for that product and that product only. And technically, for only those things that you're trying to discern with your spherical seeds as well. But everything that we do, we're customizing everything from the X-ray power all the way down to the imaging configuration whenever we set up a new project. So I'll start with our base technology. It's a flat panel detector. It's 17 inches by 17 inches. It's the same detector in a heart cath lab for an angiogram. So if you've ever seen one of those videos, chances are you've seen like the dye being injected into the vein, and you see 2 or 3 beats of the heart and where all the dye goes. And then the doctor's able to go in and do all of their stent work. Same detection that we're using for this. And it's not a detector in the sense that there's anything that's automated as it relates to it. It's a detector in the sense that we're just taking the energy from the X-ray and the product making the best image we can. So we have over 65,000 levels of grayscale that we can achieve, 2 to the 16th power. There's not a single inline X-ray that's leveraging that. We're not pixel binning anything. Everything we're getting just a straight raw image, the best image quality that you possibly can get. And if you've seen the image at one of our facilities, you understand exactly what it looks like, especially if all you've seen is the composite image on your inline machine and what it spits out. And sometimes those are extremely difficult, even whenever you see a reject on one of those screens. This allows us to be super flexible. We can manipulate KV and MA, we can manipulate contrast, we can manipulate pixel binning. If we need to, if you were looking for something that was an entire washer that got lost, we can pixel bin to speed up the process a little bit. But everything that we do as it relates to this, and this is where it all starts, is customized for the situation to try to contain this incident. The next thing that we've gone into is photon counting, and Brian from Grayscale will talk a lot more about this later. But essentially, whenever we're translating energy levels to an image, from X-ray physics, from photon energy, all the way down to the black and white grayscale image that we see on a monitor, we're playing a game of telephone, so to speak, from a physics standpoint and an energy transfer standpoint. So as we translate physics, the X-ray physics, into light energy, and then to an electrical signal, and then to an actual image, there's noise that happens as we make that translation. Photon counting has removed the biggest source of that noise, a scintillator, in that energy translation. So we can go direct from understanding the photon energy as it passes through the product and the foreign object, and can go as close to a direct image. In fact, this is called direct conversion. All other versions of X-ray imaging are called indirect conversion because you pass it through a scintillator. So Brian will talk a lot more about that later. CT technology is where we're at right now with our largest automated piece of equipment, and we have one of these devices at every single one of our facilities. They're installing our final facility in Pennsylvania is receiving theirs starting next week. It does have some limits. We're passing so much energy through this device because we're spinning a gantry 24 RPM. We have over 20 imaging devices that are inside this gantry as well, collecting data from the X-ray itself, because we're recreating a 0.5 millimeter slice of the product on an X, Y, and Z axis. So tons of data, way more data than any inline device is producing. So in order to interpret that image cleanly, we're at 160 kV and 5 MA. That's almost 1,000 watts of power. And there's not a single X-ray device in any one of your facilities that's probably pushing 600 watts. So a lot of energy going through this in order to recreate the image. Because of that, the photon power will blast through tiny objects. So as we get to like 0.7 and below, there are some limitations with detection sizes as it relates to it. This is the fastest thing that we use at FlexXray, and it's 20 feet per minute, so it's 5 times faster than our existing technology. We think it's amazing. We can process a truckload in under 2 hours of product now that might have taken us 6 hours previously. But I say all of that, and everybody's like, that still sounds absolutely slow. It is, from a food manufacturing perspective. The thing that CT benefits us the most, though, is in detection of gaskets and plastics. The biggest problem in a 2D inspection is the overlapping layer of product effect and being able to find something that's very close to the density of the product itself and separate those things out. With CT technology, we can peel back. This is a bag of chicken nuggets from the Golden Arches. And there is a 1.5 millimeter and a 2.5 millimeter piece of O-ring that's inside of this. And we're able to, because we can just peel back all of the product layering effects and look at a single 0.5 millimeter slice at a time, we're able to pinpoint and locate things that are otherwise invisible with regular technology. It also does fantastic at glass and glass detection. This is big from a European market perspective for us, not as big in the United States. We use canned goods more frequently, but we can segment a tray pack of jars with the AI machine learning capabilities of the CT, know exactly where the lid profile is, the shape of the jar. It can learn that on one case of product, ignore the jar, and only inspect inside of each individual unit within the tray pack. It's amazing. And it does that in less than 15 seconds. And then inspects every single container. So if you have issues with glass and glass, because with the two-dimensional X-ray, even if you're using a side shooter, if you have glass and glass, anybody in the room, it's difficult. There's locations around the baffle, locations where glass just has a tendency to hide from a density perspective inside the product zone. With CT scanning, we're able to remove a lot of those issues. Just to drive the point home about the two-dimensional X-ray and three-dimensional X-ray and what that looks like. So this is a two-dimensional X-ray on the left of the next few images. This is a Buna gasket. That's fairly low density. It is X-ray detectable to a certain extent, depending upon the additive that was placed in there. That's a whole different conversation about trying to fix the industry's detection standards with plastics and make it real standards of identity. We can meet afterwards and talk about how we form a group to fix that issue later, though. There was 3 millimeters of gasket that we were able to find from a CT standpoint. It's lost in the two-dimensional image because we have every single layer of this product. This, in fact, is a 40-pound box of sausage crumbles. It's 11 inches tall. It's very difficult to scan and see with the two-dimensional X-ray. Peel back all of the layers, we can find exactly where the gasket's at with the CT scanner. Shredded cheese from a dairy perspective, the raw image with shredded cheese is extremely difficult to see because of all the layering effect, especially with things like a fine shred. So we were able to find sifter wire less than 4 millimeters in length in this project. It's a little difficult to see as we zoom in here. It does have an amorphous shape around the detection. But because CT is looking at an X, Y, and Z image, it doesn't matter what the orientation of that wire is. We may have found that one piece of wire in a two-dimensional inspection, but only if it was stacked vertically so that we can have all of that above the same pixel. With CT, we can recreate that effect in any dimension. And then lastly, something a little bit different here, but a box of frozen taquitos. We were looking for just rubber gasket from the customer. We don't know what this one was made out of. They just provided us a sample. We embedded it in the product zone and demonstrated that we could, in fact, see this. This turned into around 20 truckloads from an inspection standpoint because the ingredient that it came from was in tamales, taquitos, tacos, and something else as well. So just to drive the point home about supplier monitoring and the issues that those things can create. We do all of our testing for CT inspection in the product zone. So unlike whenever we're validating an inline X-ray or metal detector where we're looking at leading and trailing edges of products just to make sure that we're timing detection and rejection up, from a CT standpoint, we actually have the ability, in fact, we want to ensure that we place it in the middle of the product zone where we're going to have the most interference from product at any angle with the gantry when we're exposing the photons to the foreign material, that we still can achieve detection. So even during a live inspection, our operators are embedding a seed card, wrapping that master case in clear red tape. We've got freezers at every single production line where they store seed cases during an inspection. But this is what the image that the operator sees whenever we reject that. I went through that a little bit faster than I had planned because I do want to give Brian and Andreas a little bit more time. I know that you want to understand a little bit more about microwave technology and photon counting, and I'm sure you'll have more questions after they go. So I'm a little bit ahead schedule. I hope I'm a little bit ahead of schedule. But if you do have any questions at this point in time, I'll pause for a moment before I do turn it over.
So the glass example that you get, does that go for like the plastic and the same type of plastic? Or is there any like or is that just for glass? Like, you know what I'm saying? Like if you have a container made of that type of plastic and a piece of that plastic was in there, can it detect that as well?
Plastic, from a packaging material standpoint, is problematic in and of itself. It does not have enough density in order to be discerned by the current version of X-ray technology that we're using. We're in an R&D state right now as it relates to low density plastic detection. I think we're still probably another iteration away before packaging materials come into that. But no, glass, we can detect glass inside of glass because the glass itself is detectable from an X-ray standpoint. We can't detect packaging material inside of a package because the packaging material isn't dense enough to discern. So, yes, ma'am.
Yes. So this is very exciting to see the advances in the technology, first of all. The question that I have is, you talked about being able to discern materials that are similar. So when I think about that, I think about things like blends. So spice blends as examples, the difference between a peppercorn and a stem or things like that. Now, I realize that that's extremely difficult, but can you give me a little bit of information or color about where we're headed with regard to that type of detection?
On the X-ray side, we're not close to that. With hyperspectral imaging, so long as we can produce a good surface area distribution of the product, there is high opportunity for shells, stems, things like that to be trained, to be understood that that's different from the product matrix itself, and to reject those. Microwave also has some good capabilities there as well. It depends on the product environment itself, the size of the piping system, different things like that, which Andreas will talk a little further about later. On the X-ray side, unfortunately, we're not there yet. They're probably 2 iterations away, similar to the low density, more like packaging material level, low density discernment. I think the next iteration will be low density, but it'll be things like, Buna and, FHK, Viton, things like that we're all struggling with right now because they're effective pieces for our engineering and maintenance teams to use, but they're not great from a detection standpoint. And we can't just throw a Teflon gasket everywhere in every system from a cost standpoint, even though it is the best thing to use for plastics detection.
And then that leads me to part of the question is how do we think them?
We need to throw all of it out and get rid of it everywhere we possibly can. We've worked with some companies that do embedding of things, whether that's a chemical marker or with filings or shavings, and everybody's been sold something by one of these vendors at some point in time, and it either was cost prohibitive or it failed miserably and disintegrated into a million pieces, and not all of it was detectable the way that they said that it was. And so there needs to be better work from us as an industry to push standards of identity as it relates to what makes something truly detectable, and not only detectable, how do we ensure that it holds up in our production and sanitation and processing environments at the same time. So we can do things to UHMW to make it more effective, but UHMW by itself will be one of the later things that we pick up from a detection standpoint.
Okay, it's almost stupid questions. Is this presentation going to be shared? At least,
I'll ask Kurt that question, but okay.
Anyways,
and then this hyperspectral, the same things optical sorting.
It's more than just that. So optical sorting still is mostly at RGB values. Hyperspectral is adding just more wavelengths from a light standpoint into the NIR range as well to that. So it's improving that by, well, to talk to Christian later, but say it's probably 10x the amount of data that we're getting from hyperspectral, if not more. Okay, thank you very much.